Imagine a machine that could solve problems impossible for today's supercomputers. A machine that could simulate molecules with such precision, it might create new medicines in days instead of decades. A machine that could transform cybersecurity, optimize global supply chains, and unlock mysteries of the universe. This machine is not science fiction. It is the quantum computer. For decades, quantum computing was a dream known only to physicists. Today, it is emerging as one of the most revolutionary technologies of the 21st century. Tech giants, universities, and governments are racing to build it. But what exactly is quantum computing? How does it differ from the computers we use every day? And how will it change the future of technology and human life? This is the story of the hidden power of quantum computers. Ordinary computers use bits, represented as zeros and ones, to store and process information. These bits are like switches, either on or off. Quantum computers use quantum bits, or qubits. Qubits are not limited to being 0 or 1. Thanks to the principle of superposition, a qubit can exist in multiple states at once. This means quantum computers can process vast numbers of possibilities simultaneously. Another property, entanglement, allows qubits to be linked so that the state of one instantly affects the other, no matter the distance. This creates powerful correlations that classical computers cannot match. Together, superposition and entanglement give quantum computers their extraordinary potential. To understand quantum computing, we must look at the strange rules of quantum mechanics. At the scale of atoms and particles, nature behaves differently from the everyday world. Particles can act like waves. They can be in multiple places at once. Their properties may remain uncertain until measured. This uncertainty is not a flaw. It is the foundation of quantum theory. Physicists like Albert Einstein, Niels Bohr, and Richard Feynman debated these ideas. Feynman later proposed that if nature is quantum, then perhaps computers should be quantum too. Quantum computers harness these principles not as curiosities, but as resources. They transform uncertainty into power. Constructing a quantum computer is one of the hardest engineering challenges in history. Qubits are fragile. They lose their quantum state through a process called decoherence when exposed to heat, vibration, or electromagnetic noise. To protect them, most quantum processors are kept near absolute zero, colder than outer space. Different technologies compete. Superconducting circuits, used by companies like IBM and Google. Trapped ions, used by IonQ and Honeywell. Photonic qubits, harnessing light particles. Even topological qubits, a more theoretical approach. Each method has strengths and weaknesses. All face the challenge of scaling from dozens of qubits to thousands or millions, where real breakthroughs will occur. Quantum computing is still in its infancy, but progress accelerates each year. In 2019, Google announced it had achieved quantum supremacy. Its quantum processor performed a task in 200 seconds that would have taken a classical supercomputer thousands of years. While the task itself had little practical use, it proved that quantum computers can outperform traditional ones in specific cases. Since then, progress continues. IBM has developed processors with more than 1,000 qubits. Startups are exploring error correction techniques to stabilize computations. Governments are investing billions of US dollars in quantum research. These early milestones mark the dawn of a new era. One of the most exciting applications of quantum computing is in medicine. Drug discovery today often requires years of trial and error. Quantum computers can simulate molecules at the quantum level, predicting how they interact with proteins in the human body. This could accelerate treatments for diseases like cancer, Alzheimer's, or viral infections. In materials science, quantum simulations could design new alloys, superconductors, or batteries. This might lead to more efficient renewable energy, lighter aircraft, or better medical devices. By unlocking chemistry at its deepest level, quantum computing could transform industries that shape our lives. Quantum computing is not only about science, it is also about business. In finance, quantum algorithms may optimize investment portfolios, detect fraud, and model market risks with unprecedented accuracy. In logistics, They could optimize global shipping routes, air traffic, and supply chains, saving billions of US dollars and reducing environmental impact. In artificial intelligence, quantum computing may accelerate machine learning, allowing AI to process complex data faster and more effectively. This synergy between quantum computing and AI could open entirely new technological frontiers. Quantum computing will not replace classical computing, but it may supercharge it. Quantum computing also brings risks. Most of today's encryption relies on mathematical problems that classical computers cannot solve in reasonable time. A large enough quantum computer could break these codes quickly. This would threaten everything from online banking to national security. To prepare, researchers are developing post-quantum cryptography, new algorithms designed to withstand quantum attacks. Governments and tech companies are already testing these systems to secure the future digital world. The race is not only to build quantum computers, but also to protect against them. When will quantum computers change the world? Experts disagree. Some say within 1 decade. Others believe it may take several decades before large-scale, fault-tolerant quantum computers become practical. What is certain is that progress is steady. Each breakthrough brings us closer to machines that will reshape science, medicine, finance, and technology. Quantum computing represents a new chapter in human innovation. It challenges us to rethink what is possible and to prepare for both opportunity and disruption. The future may belong to those who harness its hidden power. Quantum computers are more than machines. They are the embodiment of human curiosity, imagination, and determination. They remind us that nature, at its deepest level, is strange, unpredictable, and full of potential. The journey to build them is one of the greatest scientific discoveries of our time. And when their hidden power is unlocked, they will change technology, industry, and perhaps even our understanding of the universe itself. Long before modern computers, the seeds of quantum thinking were planted by the giants of physics. In the early 20th century, Max Planck and Albert Einstein uncovered strange truths about light and energy. They discovered that reality at the smallest scales behaves in discrete packets, quanta. Then came Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, who revealed that particles could exist in many states until observed. Their discoveries shattered the classical worldview. By the mid-20th century, physicist Richard Feynman realized something profound. He said, "Nature is not classical. If you want to make a simulation of nature, you had better make it quantum mechanical." That statement became the inspiration for the field of quantum computing. It was no longer a question of if computers could harness quantum behavior, but when. To understand why quantum computing is revolutionary, imagine a maze. A classical computer must test one path after another until it finds the exit. A quantum computer explores all possible paths at once. This is because of superposition, a qubit existing in multiple states simultaneously, and interference, which amplifies correct answers, while canceling out wrong ones. Together, these properties allow quantum computers to solve certain types of problems exponentially faster than any traditional system. Tasks that might take billions of years for classical machines could, in theory, take minutes for quantum processors. This is not just faster computing. It is an entirely new way of thinking. Building a quantum computer is a masterpiece of engineering. Inside the laboratories of IBM, Google, and D-Wave, machines sit inside gleaming metal cylinders that look more like art installations than computers. These are dilution refrigerators, cooling the processors to near absolute zero, about -273 degrees Celsius. Every qubit must be isolated from vibration, light, and electromagnetic noise. Even the smallest disturbance can destroy its fragile quantum state. Engineers use vacuum chambers, laser traps, and magnetic shielding to stabilize each atom, electron, or photon. The control systems are equally sophisticated. Thousands of microwave pulses guide qubits through precise operations measured in nanoseconds. Every flicker of energy must be perfectly timed. These machines are not simply built. They are orchestrated like instruments playing at the edge of physics itself. Even the most powerful hardware is useless without the right algorithms. Quantum computing introduces a new language of logic, where problems are solved through interference patterns instead of linear steps. The most famous example is Shor's algorithm, created by Peter Shor in the 1990s. It can factor huge numbers exponentially faster than classical methods, the reason encryption experts worry about quantum security. Another is Grover's algorithm, which accelerates database searches. Today, researchers design hybrid algorithms that combine quantum and classical computing, using quantum processors to handle complex mathematical cores, while classical systems manage overall logic. These algorithms will shape industries as much as the hardware itself. They are the software of the quantum age. At the heart of quantum computing lies the ability to simulate quantum nature directly. Classical computers struggle to model molecules because each particle interacts with every other particle, a challenge that scales exponentially. Quantum computers can mirror these interactions naturally. Researchers at companies like IBM, Microsoft, and pharmaceutical firms use early quantum prototypes to model caffeine molecules, catalysts for cleaner fuels, and potential antiviral compounds. In the near future, this ability could revolutionize drug design and materials engineering. New superconductors may emerge that work at room temperature. Solar panels may become twice as efficient. Quantum computing might enable an entirely new generation of discovery-based industries built on simulation rather than experimentation. Artificial intelligence and quantum computing are two pillars of the next technological revolution, and their intersection is explosive. AI thrives on massive data, but classical computers face limits in processing it. Quantum systems could search and analyze these vast datasets at unprecedented speeds. Quantum neural networks, still experimental, aim to mimic human cognition more efficiently by operating on superposed data states. Imagine AI models that learn faster, recognize complex patterns instantly, and generate simulations that predict human behavior or natural processes in real time. Quantum AI could redefine everything from weather forecasting to autonomous robotics. Some experts call this convergence the intelligent singularity, where quantum-enhanced AI reshapes innovation itself. Cybersecurity is entering a new battlefield. Every nation and corporation is racing to develop post-quantum encryption, knowing that whoever first builds a powerful quantum computer could theoretically unlock all existing digital secrets. Quantum key distribution is one defense. It uses quantum particles of light to transmit encryption keys. Any attempt to intercept them instantly changes their state, revealing the intrusion. China, the United States, and Europe are testing QKD networks, linking cities by satellite and fiber optics. In this new digital arms race, trust will depend on quantum laws of nature rather than human secrecy. The economic impact of quantum computing could be staggering. Analysts predict it may generate trillions of US dollars in value across industries. Banks could model risk in real time. Energy companies might optimize grids at planetary scale. Manufacturers could design zero-waste production systems. Quantum computing may also give rise to quantum as a service, where cloud platforms rent quantum power to businesses, just as they do with traditional servers today. Countries investing early in quantum ecosystems, the United States, China, Japan, and Germany, may define the next century's technological balance of power. This is not just a scientific revolution. It is an economic one. What happens when humanity masters computation at the quantum level? Some physicists believe quantum computing could one day help us model entire universes, understanding gravity, black holes, and the origin of space-time itself. Quantum simulations might recreate the conditions of the Big Bang, or predict how dark matter behaves. Others envision quantum networks linking computers across the planet through entangled particles, creating the quantum internet, a communication web faster and more secure than anything before. In this future, data will not travel as signals, but as entangled information across space and time. Quantum computing may not only change technology, it could reveal the hidden architecture of reality. If you enjoyed this journey, subscribe for more cinematic explorations into science, discovery, and the future of technology.